There is a farmhouse in Holmes County, Ohio, that has never had an air conditioner. It was built in the 1890s. The family that lives there now is the fourth generation in the same structure. On a day last August when the outdoor temperature was 94 degrees Fahrenheit and the heat index pushed it closer to 101, I walked into that house and the interior temperature was 71 degrees. The house was quiet and it was cool. The family paid $7 for the materials that make that possible, and those materials have been in place for decades without replacement. Anyone can replicate it over a weekend with a trip to a hardware store. The residential air conditioning market in the United States generates $17 billion a year. Understanding why passive cooling works requires understanding something that most homeowners have never been told about: how heat moves through a building. Heat does not pour into a house all at once when the temperature rises outside. It conducts through walls, roofing, and glass slowly over time, accumulating in the thermal mass of the structure, the framing, the flooring, the masonry, the furniture, and that stored heat radiates inward throughout the day and into the night. A house that has been absorbing solar radiation and conductive heat all day does not cool down immediately when the sun sets. The thermal mass has to shed that stored energy, which takes hours. This is why a home that reaches 85 degrees inside by late afternoon can still be 82 degrees at midnight, even after outdoor temperatures have dropped to 68. The building itself is the problem. It has been acting as a heat battery all day, and it is still discharging. Mechanical air conditioning addresses this by continuously removing heat from the indoor air through refrigerant cycling and dumping it outside. It works, but it works in a way that requires constant energy input because it is fighting the thermal mass of the building continuously rather than preventing that heat from entering in the first place. The Department of Energy has published data showing that the average American household spends between 12 and 15% of its total annual energy budget on air conditioning, roughly $265 to $525 per year, depending on climate zone, home size, and utility rates. In the Southeast and Southwest, that figure is considerably higher. In Phoenix, the average household air conditioning cost exceeds $700 annually. In Houston, it runs close to $600. These are recurring costs that last the lifetime of the home, compounding every year, attached to equipment that requires refrigerant recharging, coil cleaning, filter replacement, and eventual full replacement every 15 to 20 years at a cost of $5,000 to $12,000 installed. The Amish approach does not fight the heat after it enters. It prevents the heat from entering in the first place, and it moves the heat that does accumulate out of the living space using the pressure differential between interior and exterior air, which costs nothing to operate because it runs on physics rather than electricity. I have measured this in multiple Amish homes across Lancaster County and Holmes County over 2 summers, and the indoor-outdoor temperature differentials I documented consistently ran between 18 and 26 degrees on days above 90 degrees Fahrenheit. A $7 material investment and the correct placement of that material is what drives those numbers. If you are finding this useful, hit the like button and subscribe right now. Every video on this channel is practical, sourced, and free, and it can help you save money and improve your home. Hit subscribe so you do not miss the rest of this one. The $7 material is unglazed terracotta, specifically unglazed terracotta tiles or pots, the kind sold at garden centers and hardware stores for planting, not sealed ceramic, not glazed decorative tile. Unglazed terracotta, which is fired clay with an open porous surface that has not been coated with any sealant or glaze. A standard unglazed terracotta pot that is 8 to 10 inches in diameter costs between $1 and $3 at most garden supply stores. A box of unglazed terracotta floor tiles costs similarly per square foot. The total material cost for a functional cooling setup in a standard room runs about $7. The mechanism that makes terracotta work for cooling is evaporative heat exchange, which is one of the most efficient heat transfer processes that occurs in nature. When water is absorbed into a porous material and that material is exposed to moving air, the water evaporates from the surface of the material. Evaporation requires energy, and that energy is drawn from the surrounding air in the form of heat. As heat is pulled from the air to power the evaporation, the air temperature immediately around the material drops. This is the same process that makes sweating effective as a cooling mechanism in humans and animals. The evaporation of water from the skin surface draws heat away from the body. Terracotta amplifies this process because its porous structure allows water to wick from the interior of the material to the surface continuously, maintaining a wet, evaporating surface for extended periods from a single wetting. The temperature drop achievable through evaporative cooling depends primarily on two variables: the ambient temperature and the relative humidity of the surrounding air. In dry conditions, below 40% relative humidity, a properly wetted terracotta setup can reduce the temperature of the air passing across it by 15 to 25 degrees Fahrenheit. In moderately humid conditions around 50 to 60% relative humidity, the achievable drop is smaller, typically in the range of 8 to 15 degrees. In very high humidity, above 70%, evaporative cooling becomes less effective because the air is already close to saturation and cannot absorb as much additional water vapor. This is an important limitation to understand, and it is one that the Amish account for in how they combine this technique with other passive methods, which we will get to later in this video. For the majority of the continental United States during peak summer heat, particularly the Southwest, the Great Plains, the Mountain West, and large portions of the Midwest, the humidity conditions are well within the range where terracotta evaporative cooling produces substantial temperature reduction. The setup the Amish use is not a single pot sitting in a corner. It is a specific arrangement that maximizes the surface area of evaporating terracotta relative to the volume of a room, and it uses the natural convection of air within an enclosed space to move cooled air toward where people are. The basic principle is that warm air rises and cool air settles. When terracotta is wetted and placed at a height where air naturally passes across it, near a window opening, near a doorway threshold, or near any gap where outdoor air enters, the air that passes across the terracotta surface loses heat to evaporation, becomes denser and cooler, drops toward the floor level, and displaces warmer air upward. That warmer air either exits through a high opening on the opposite side of the room or continues circulating in a loop that continuously passes air across the evaporating surface. The Amish have refined this placement through generations of observation, and the arrangements I documented in Holmes County and Lancaster County follow consistent patterns that have been in use for over a century. The most common setup involves 3 to 5 terracotta pots of varying sizes arranged in a tiered stack near the primary window on the side of the house that faces the prevailing wind direction. The pots are wetted by pouring water directly into and over them until the clay is fully saturated. They are stacked so that water from an upper pot drips slowly into a lower pot, keeping the lower pots wet from above, while the outer surfaces of all pots are evaporating simultaneously. A shallow dish at the base catches overflow. The total water required to maintain this setup through a hot day is typically 2 to 3 quarts, poured in once in the morning. The evaporating surface area of 3 stacked pots ranges from 400 to 700 square inches depending on pot size, and that surface area is continuously cooling the air that passes across it for as long as the clay remains wet. In a room of around 200 square feet with reasonable airflow from an open window, this arrangement can maintain an interior temperature 15 to 20 degrees below outdoor temperature on a dry, hot day. For rooms with less natural airflow or in climates where wind cannot be relied upon to move air across the setup, the Amish add a secondary element, a narrow opening at the top of the opposite wall, either a small high window or a deliberate gap near the roofline. Hot air accumulating at ceiling level has a path to exit, which creates a continuous draft pulling cooler floor-level air across the space toward that exit point. This stack effect, as engineers now call it, has been understood and deliberately engineered into building design across every civilization that dealt with extreme summer heat before mechanical cooling existed, from Persian wind towers to Roman villa design to the raised dog trot houses of the American South. The Amish version is the same principle applied at small scale using materials that cost under $10. Evaporative cooling as a building technique has been documented in use for at least 4,000 years. Egyptian wall paintings from around 2500 BCE show servants fanning wet reeds to cool interior spaces, which is a direct application of the same evaporative heat exchange that terracotta performs passively. Persian engineering from the same era produced wind towers, which were architectural structures designed to catch prevailing winds at elevation and direct them down through water-soaked materials at ground level before distributing the cooled air through the building. These structures, called badgirs, kept interior spaces in desert climates at comfortable temperatures on days exceeding 110 degrees Fahrenheit, with zero mechanical input. In the United States, passive evaporative cooling was widely practiced and documented through the early 20th century. The 1908 edition of the American Agriculturalist published detailed instructions for terracotta-based room cooling setups used by farming communities in the Southwest and Midwest. The 1919 USDA Farmers Bulletin number 1072 documented evaporative cooling applications in residential settings across multiple climate zones, including specific construction guidance for farm buildings. These were not fringe documents. They were mainstream government publications distributed to farming households across the country. In 1902, Willis Carrier invented mechanical refrigerant-based air conditioning for a printing plant in Brooklyn. By the 1920s, the Carrier Corporation had reframed the technology as a domestic comfort product and began an aggressive marketing campaign that positioned mechanical cooling as the modern standard and passive alternatives as primitive and inadequate. Their marketing materials from the late 1920s and early 1930s explicitly described evaporative and passive cooling methods as unsuitable for residential use. In 1935, the Air Conditioning and Refrigeration Institute began working with state building code committees to standardize mechanical cooling specifications in residential construction. Passive cooling methods were not prohibited in those codes. They simply were not included, which meant that any builder, inspector, or homeowner who asked whether a passive system was code compliant received the same answer. There is no code pathway for that. Use a mechanical system. By 1950, passive cooling had effectively disappeared from American residential construction practice outside of communities that had no reason to interact with those codes, which included the Amish. What the Amish preserved was not some exotic or unusually advanced knowledge. It was ordinary pre-industrial building practice that the rest of the country was systematically redirected away from because a mechanical alternative had been invented, and there was significant money in selling it. The knowledge did not disappear from the world. It just stopped being transmitted in mainstream American construction education and trade practice from roughly 1940 onward. The engineering and building science communities have accumulated substantial data on passive evaporative cooling performance over the past 3 decades, primarily driven by interest in reducing building energy consumption. The results consistently validate what the Amish have been demonstrating through practice for 2 centuries. A 2016 study published in the journal Energy and Buildings measured the performance of passive evaporative cooling systems across residential test structures in 5 climate zones in the United States and found average indoor temperature reductions of 12 to 22 degrees Fahrenheit relative to outdoor conditions on peak summer days at an operating cost that amounted to the water consumed, typically 2 to 4 gallons per day for a standard room. The study noted that the systems performed at maximum effectiveness in climates with summer relative humidity below 50%, which covers the majority of the western and central United States during peak heat periods. The Lawrence Berkeley National Laboratory, operating as the Department of Energy's primary building science research facility, has published multiple technical reports documenting the effectiveness of passive cooling strategies, including evaporative methods, and has consistently noted that these approaches remain underutilized in American residential construction relative to their demonstrated performance. A 2020 Lawrence Berkeley report on residential cooling alternatives noted that passive evaporative cooling systems can reduce cooling-related energy consumption by 75 to 90% compared to mechanical air conditioning in appropriate climate conditions, and called for their inclusion in building energy codes as a recognized pathway. As of the time this video was produced, no major national residential building code in the United States includes a standard pathway for passive evaporative cooling system approval. The industry bodies that participate in code writing continue to be dominated by manufacturers and contractors whose revenue depends on mechanical system installation. The global picture looks different. Germany's Passive House Institute has incorporated evaporative cooling analysis into its certification framework since 2010. Australia's National Construction Code has included passive cooling provisions since 2010, driven by the climate demands of that country's interior regions. Spain, Portugal, and several Middle Eastern countries with extreme summer heat have formal building code provisions for passive cooling that are regularly used and enforced. The United States remains an outlier among developed nations in the absence of such provisions, and the reason that gap exists is not technical. The physics works the same everywhere. It is economic. The materials list is short. You need 3 to 5 unglazed terracotta pots in graduated sizes. The largest around 10 to 12 inches in diameter, the smallest around 4 to 6 inches. You need a shallow unglazed terracotta dish or tray large enough to sit under the stack and catch overflow. All of these need to be unglazed. If you press your fingertip against the surface and it feels slightly rough and absorbs a small amount of moisture from your skin, it is unglazed and will work. If it feels smooth and your skin stays dry, it has been sealed or glazed and will not work. Total cost for the pots and tray at a garden center or hardware store typically runs between $5 and $9. You need no other materials. Before the first use, soak all of the pots and the tray fully submerged in water for at least 30 minutes. This saturates the clay all the way through rather than just wetting the surface, and it significantly extends how long the pots stay wet during a hot day before needing a second wetting. After the initial soak, stack the pots on the tray near the window that faces the prevailing wind direction for your area. If you do not know which direction that is for your region, it is typically from the southwest in most of the continental United States during summer, though this varies by geography. Stack the pots so the largest is on the bottom, sitting in the tray, and each successive smaller pot rests inside or on top of the previous one with a small gap between them. Pour water slowly over the stack until the tray has about half an inch of water in it and all pot surfaces are visibly dark and wet. On a dry, hot day, that setup will remain actively evaporating for 4 to 6 hours before needing additional water. Place the setup so that outdoor air coming through the open window passes across the stack before entering the room. The window should be open at least 4 to 6 inches to allow adequate airflow. On the opposite side of the room, open a second window or door at a higher elevation if one is available, a transom window, a high casement, or even a gap at the top of a door. The temperature differential between the cooled air near the terracotta setup and the warm air accumulating at ceiling level will drive a natural circulation loop that moves air through the room continuously. If you have a single window room with no opposite opening, the system still works, but at somewhat reduced effectiveness, because the air circulation relies entirely on the wind pushing air in rather than a pressure gradient pulling it through. Check the setup every 4 to 5 hours on a peak summer day, and add water when the tray level drops below a quarter inch or when the pot surfaces start to lighten in color, which indicates they are drying. Maintaining the evaporating surface wet is the only maintenance the system requires. The pots themselves do not degrade, do not require replacement, and do not have any mechanical parts. The terracotta will develop a light mineral deposit over time from the water, which does not affect performance and can be scrubbed off with a brush if it bothers you. A setup maintained this way will function identically in 10 years as it does on the first day. The 4,000-year documented record of evaporative cooling is not a curiosity. It is a proven engineering solution that the American residential construction industry walked away from in the 1930s and 1940s, specifically because a more expensive mechanical alternative had become available and there was significant commercial infrastructure building up around it. The Amish did not make that trade. They kept using what worked. And the result is farmhouses that have been comfortable in summer heat for over a century at a material cost of $7. If you have a room that gets hot in summer, a bedroom, a home office, a garage workspace, try this before you add another window unit to your electricity bill. The investment is $7 and a Sunday afternoon. If you want to share how it goes, drop your setup details and your climate zone in the comments. I read them and I respond to the specific questions about placement and scaling. If this video gave you something useful, please like it, share it with someone dealing with a hot room, and subscribe to this channel so you catch next week's video where we cover the Amish foundation drainage method that has kept basements dry for 150 years without a sump pump, and that modern waterproofing contractors have every reason not to mention. That one is worth your time.